Hi, my name is Haici. The authors here are from IU and Adobe Research. This research is about music remixing, which can be defined in various ways, mostly about manipulating the level and or effects of individual instruments to create different versions of recording. Here in this paper, we target specifically on the remixing case where one wants to adjust only volume level of the different sources. As shown in the graph on the left, the user interface indicates what are the remix weights, and a neural remixer should work to produce the requested remixture. However, the task is not as straightforward as it appears. The very basic ingredients for remixing are the original stem tracks for each instrument, which are not always available. Therefore, a traditional method is to first use a powerful source separation model to separate the tracks and then apply the desired remixing weights to the separated result. However, the separation can never be perfect. Considering the case of guitar and drum separation, the reconstructed guitar will remain some drum and produce some artifacts, and likewise, the drum will contain some guitar leftover and some different artifacts. If we just simply regale and add them up together, firstly, the artifact will add up and be more salient because they don't cancel out each other. And secondly, because of the interference contained here, the output remixture result will not be coming out close to the desired remixture. Therefore, in this paper, we provide a solution to the problem. To summarize in one sentence, don't separate, learn to remix. Instead of keeping the separator, we want to design an end-to-end neural remixer to implicitly separate and remix. With that said, a powerful separation model is still needed in this research to form a baseline model, and also from it, we'll also derive our proposed models. Our choice is ComTestNet. Debuted in 2019, it is at the time the most powerful separation model running on the time domain. Till today, it still shows a top quality music separation performance. And more importantly, ComTestNet provides a special setup that a latent space is learned for a masking-based separation. This diagram shows how ComTestNet works. The encoder maps the input waveform to a latent space, and a separation mask generated by the separator module is applied to the latent features to produce a separated latent variables, which are then decoded back to the time domain sources. This architecture gives us a way to manipulate the latent space in the proposed models, which I will dive deeper in the next few slides. We use the default setup of ComTestNet as in its original paper, except that during training, we replaced the scale invariant SDR with regular SDR as the objective function to let the model be scale insensitive for generating correct remixing results. Our baseline is a realization of these conventional remixing methods, where the separation and the remixing procedures are totally independent. We use a ComTestNet to firstly separate the sources, which as indicated by the previous slides, and then the output remixture is the weighted sum of the sources, where the weights can be arbitrarily defined by the users. Here I will play some examples of amplifying the string source, which is also the other source in the MuseDB dataset, by 12 dB. Firstly, I will play the original mixture and the target remixture and the output from the baseline. I want you, we shouldn't be lonely, we shouldn't have doubt. Now is the target remixture. I want you, we shouldn't be lonely, we shouldn't have doubt. Where the string source has been boosted. And now I want you, we shouldn't be lonely, we shouldn't have doubt. You'll notice that the artifact here contained in the baseline output is quite obvious. And more importantly, you don't feel that the string source in the baseline has been boosted as desired by the users. We have talked about the artifact and interference trade-off contained in the baseline model. Now we have two solutions in this paper. The basic idea behind them is to let the separation model be aware of the intent of remixing. Model 1 did that by jointly optimizing the separation model, not only toward the objective of separation, but also the objective of remixing. Meaning the loss function showed in this blue box should contain a separation loss and a remix loss. And by having this additional loss term, the model learns to produce some separation results that are better for remixing use. We experimented different ratios for these two loss terms, and we provide 3 examples in the paper. Here they are listed in an ascending order of the impact of remix loss for the model training. In this very extreme case where lambda equals to 0, the entire model is solely trained to optimize the remixing target. On top of the joint optimization performed in model 1, model 2 further adapts the separation model to remixing by multiplying the remixing weights directly onto the latent features, as indicated by the green lines in the diagram. Now, because the latent features have already been scaled, the model will output the scaled source directly. The potential advantage of model 2 over model 1 is it actually passes the remixing intent to the feed-forward process, so that even at the inference stage, the decoder of model 2 can be repurposed for better remixing configuration. And again, here we provide the remixing examples of increasing the strain source by 12 decibel. I'll again first play the baseline and come to model 1 and model 2 output. I want you, we shouldn't be lonely, we shouldn't have doubt. Now, model 1, sorry. I want you, we shouldn't be lonely. Model 2. I want you, we shouldn't be lonely, we shouldn't have doubt. You can hear that model 1 and model 2 apparently did a better job controlling the artifact and rendering a more accurate perceptual remixing scales. We did our evaluation on NewsDB and Slack dataset and also considered cross dataset testing just to evaluate how well our model can generalize to other datasets. We focus on the remix task, which is different from separation. As a result, we have specialized evaluation metrics that are unique to typical separation works. There are basically 2 properties that we care about. Firstly, how well does it sound, and how cracked the result sounds in terms of the remixing scales. Firstly, we use mean SDR to measure the reconstruction quality. Mean SDR here represents for the minimum value of SDR and SD-SDR. It is suggested by LaRue in the paper SDR half-baked or well done as a more accurate way of reporting the reconstruction quality under the consideration of source scales. Also, we have loudness difference to measure the difference of the loudness scales between the target and the prediction. This number tells you whether the output remix truly reflects the desired remixing scales, and we want this number to be as small as possible. The table you're looking at summarizes the remixing quality scores for all the experimental cases, including the different numbers of the sources and 3 loss weight ratios for each of the models. There are 2 important findings in this paper. In general, both model 1 and model 2 achieve a better remix quality and smaller loudness difference than the baseline. And this improvement is more significant as the number of the sources increases. And secondly, the remix-only loss is preferred in most of the cases when K, which is the number of the sources, equals to 2 and 3, which echoes our title, Don't Separate and Learn to Remix. Of course, when the number of the sources increase to 4, and that's when the task gets harder, it is beneficial to have a higher separation control, although the model still prefer to have the dominant remix loss. Although separation is not the target of this paper, it's still useful to check it out how the separation perform to better understand the behavior of our remixing model. We compute the improvement of SDR, SIR, and the standard SAR for the 3 model separation results for both datasets in the 4-source remixing case. Without any remix loss, the baseline doesn't do well in recovery some instruments, for example, piano and guitar in the FLAC experiments and vocal and bass in the MuseDB case. And look at the significant improvement over most of the instruments on all of the scores. The graph assures us that our neural remixer can successfully benefit from the joint separation remixing objectives, where the remixing loss actually works like a regularizer that helps improving SAR score and SIR simultaneously. We are also curious about how does the remix performance change with the remixing weights. The x-axis here in both graphs are the adjustment level of vocal from -24 decibel to +24, while the other instruments are kept unchanged. Our proposed model, which are represented by the red and blue lines, outperforms the green line baseline constantly in all the remixing weight choices with higher reconstruction scores and lower loudness scores. And the more interesting observations lies at the shape of these 2 plots. Taking the left-hand one, for example, when the volume control amount is near 0 decibel, the performance of proposed model reached a peak, indicating that it's producing something very similar to the input. The baseline, by comparison, is unable to produce this very most basic mixture. Its mean SDR score decreases almost monotonically as the remixing weights change. And similarly, the lowest loudness difference value for the baseline also is not obtained at the 0 dB case. And this is a sound manifest of the uncancelled artifact existing in the baseline output. By this comparison, we can say that our proposed model's performance are much more predictable. Finally, the takeaway for you. Because of the artifacts and interference, direct source separation are suboptimal for remixing. So our end-to-end neural remixer can help this issue by informing the model for remixing intention and jointly optimize separation and remixing. If you are interested in this problem, please stop by our poster and more audio samples are available on our website. Thank you.